Thanks for having me again. It's been great to be back. And I think if anything, I want to convey the message, what a great meeting this is time and time again, because my first time here was as a PhD student many years ago. And I made friends then that I still see in the room, and it was a great opportunity to learn from others, and it still is. And so I'm from New Zealand now. In Aotearoa is the Maori name for New Zealand, and the city of Auckland actually used to be called Tamaki Makaurau. And Tamaki Makaurau is built on 53 volcanoes, and it's an active interplate volcanic field. And here you can see some of those volcanoes. This volcano is called Maunga Kiakia. That means Maunga means hill, and Kiakia is a native vine. The native vine's gone. And since then, white settlers renamed the volcano One Tree Hill. And I'd like to argue that this is the most famous volcano in the world, because there's a song by U2 on the Joshua Tree, and it shows my age. If you don't know what U2 is, but I think they're still on tour, and they have a song on that album on the Joshua Tree called One Tree Hill. So we think we work on famous volcanoes, but this may be the most famous one. The most important one for the city is probably this one here. That's Rangitoto Island. It's the most recent volcano. It's 600 years old, and you can find the footprints of Maori in the ash of the local farmers that were getting away when that erupted. I'm not asked to talk about volcanoes. Hopefully you had a chance to see Hugo's poster on our efforts to understand the volcanic field better. But I came all the way together with Alex, to carry the flag for doing measurements in confined spaces. And so I'll tell you about ultrasonic waves and their geophysical applications. So that work's done with a lot of people, and here are some of the main players for today. Jonathan just graduated his PhD. He's now in Boston at MIT. The second half of my talk, I'll focus on the work he did in his PhD, and a host of other collaborators. Dylan's in the room. We'll show some of his previous work. So, quick outline. I'll show you about ultrasound experiments. I'll start with some of the classic experiments. Again, I start to sound like an old grumpy man. Don't forget about these old experiments, but they're really cool. And then some more recent experiments that we have done in the lab. And I call them tabletop experiments because they're kind of at atmospheric conditions and they can be fun and useful. And then we go into rock physics, and that's more towards applications towards that can integrate with some of the seismic results we saw here today. Okay, so when I was a student, this was the picture. I think the picture of this meeting has been Florence, a picture about nonlinear waves, and I had it lined up as well. So we'll see it come by. But when I was a student, this was a big deal, and this is an experiment done in Paris at ESPCI around the turn of the century, and this is a top view of a tank with steel rods. And a pulse was sent off on one end of the tank, and then the wave would propagate through the steel rods and come out at the other end, recorded on an array of receivers. And what you see is basically a strongly scattered wave field, multiply scattered wave field with a long coda. And then the idea was that Arnaud Turin and Matthias Fink, they turned this signal around like this, and then sent it back. If Matthias was here, he would tell you about hello and ole, usually, like turning the sound around, and then he sent it back to the rods. Now, if you ask a person on the street what would happen, you said, well, I had a pulse, I made a mess, now I'm going to turn that mess around and I'm going to send it back through the rods. I get double the mess. Yeah? But they don't know the wave equation like we do, and that they knew, and that the symmetry of that wave equation would then refocus that signal back to a point. That was an amazing experiment, and also triggered, this was one group that got thinking about this for time, that using this time reversal for the Green's function estimation. And so these are some different arrays of the rods, and it always works. The other experiment, and I couldn't find a better figure, but this by a paper by Lopkes and Weaver, or a whole series of papers on this topic. This is a cylinder. They could have done better than that, I think. But this is a cylinder, but this is the important part, and it's the circuitry attached to the cylinder. It's a transducer, a receiver, and some electronics, an amplifier, and a computer to record that. And the circuitry is important because circuitry is noisy. And this created thermal noise into the system, so there was no source. And they just had the system on with the receiver and listening constantly. And when they recorded enough data and used the autocorrelation of this receiver, they retrieved the Green's function as well. So I'd say that's the other famous classic experiment that triggered this whole idea about the Green's function retrieval. But as Michel showed earlier, it was almost a kind of a reinvention or a reimagination of that idea, as Aki and even some others had done this previously already. But for us, this was a time to start thinking about that in seismology. So after I came back from the meeting, I wanted to do these experiments too. In fact, actually, I signed up to do a PhD in inverse theory with John Scales. John did a sabbatical at ESPCI, saw the rods, and just was completely blown away and says, I want to be an experimental physicist. So he completely left the inverse theory behind. And so I had to also follow and say, okay, I'm not doing inverse theory. I'm going to do experiments now. And John saw the rods, the metal rod experiment. He said, but what about the wave field in between the rods? I wish I could get a handle on that one. So he had a big block of aluminium, like airplane grade aluminium, so it's very homogeneous inside. He had the grooves cut into that in a Fibonacci sequence to get some sort of randomness or pseudo-randomness on that. And we measured the wave field in between the scatterers. And I'll show you a little bit about that. But when I came back from the meeting, I was like, well, there was this talk about sources had to be everywhere. It's like, how can that be? We'll never get that. We'll never get sources everywhere. So I'll put two transducers on the side of this block without grooves. So this is now a homogeneous experiment. And I put two receivers on. And if I pick my source position carefully, I'll always have a direct wave. So when I cross-correlate these signals, I get a virtual source here because the cross-correlation basically subtracts the common path or the path before and leaves you this one. So you're always going to get a surface wave through, and that's why we're so good at surface wave retrieval with noise, because this is a very common situation. But if I get the distance right geometrically, I'll get a reflection here that bounces, there's a double bounce here, and when I do the cross correlation, I already with one source, I'll get a good idea about the reflected signal. And that's what you see here. So this is that first reflected signal. And in fact, I didn't draw it, but you also have already a double bounce here that gets to another double bounce here that you can also get in your Green's function from one source. I'm also missing some mode conversions when you do it with one source. But even if you add a bunch of sources, you could get really close. And I think this showed to us that you can already get really good Green's function estimations in seismic settings with only a storm or something in a convenient place, geometrically located smartly with your receivers. Then I mentioned the scattering experiments. Let's see if this works. So this is on a side of the block with one groove here. So this is a measurement. It's not a numerical simulation. We measured the wave field here, and I'll explain how in a second. And then you could see that we had an incident field, and then these waves bounce eventually off the end of the block. It's finite, and they come back here. So I think it goes on a loop, I hope. You can see it one more time. No, it doesn't. Let me try, see if I can play it one more time. I may have to just run it one more time. So I'll click it one more time. So you see the incident field, you see a Rayleigh wave, and then body wave diffractions, and a reflected field and a transmitted field. So that was for one groove. One of the sides had many grooves, and with the help of Matt knew how to understand the theory, Matt Haney. we were able to fit these data in a radiative transfer model. We had to adjust it, or Matt had to adjust the theory, because when we tried to do that, theoreticians told us in these 1D or pseudo 1D systems, radiative transfer theory doesn't exactly hold, and Matt derived the theory to fit for that. So that was really, really, really fun, and it was the time of my life really to do these experiments. And then we thought about that first experiment on the homogeneous side. What if we have a two-layered system and we have our receivers here? What if we pick our sources cleverly, and now we get at an angle, at the critical angle, we'll get refracted waves, and they'll leak into, or they'll tail off from this interface to the receivers. And if you cross-correlate that, then again, you take away the common path beforehand, and you're just left with the information along this interface here. And so this is the real Green's function, or what we measured with a true source at the first receiver. And you see the P wave and the surface wave. But if you did this by cross-correlating methods, you get the strong surface waves, not much of the P wave, but this other event here that we call the virtual refraction. And so then we had a visitor from Delft, Elmer Ruigrok, who said, oh, that's cool. What if we scale that up and we use events on a network where that's post-critical, we get refractions from the core mantle boundary. That's the P-diff phase. And it also has this same virtual refraction idea. But we made some assumptions that we knew this part of the path, so we made a correction, and then a correction for these path lengths. And any differences then left over would be due to heterogeneity close to the network. So here, this was a map then of North America, and sure enough, the differences in the travel times matched up really nicely what we know with the crustal features of North America, where this is hot and young and slow, and the East Coast is old and fast. But that's as far as the field as we're going to go, because back now to the lab as promised. After these experiments with transducers, we said, okay, if we want to measure between these grooves, we're going to need something else than a transducer. It doesn't fit, and transducers are notoriously ringy. So seismometers for the field are much better built that way, but because of the nature of transducers, they're very small, they have no backing. Transducers are ringy, so if you want to study multiple scattering, you don't want ringy signal because it interferes with the coda that you're really interested in. So we got lasers to do that. So we send now, instead of using a transducer to create the signal, we use a high-powered laser to create thermoelastic expansion on the sample, and that creates our wave field. And that is then transmitting through or anywhere really, but this is in transmission mode. We can shine another laser at the surface, and that measures a Doppler shift. So this is a continuous wave laser, not a pulsed one, of a single color. And if the surface moves, then the reflected signal is Doppler shifted. This is exactly the same. Oh, I think we just saw a way to get speeding tickets by using DAS. This is actually how the police do it. Yeah, they shine not in the optical wavelength, but in the radar wavelength. This is how you get your speeding ticket, because they shine these at your bumper. So the nice thing about this no ringing, we can put these beams on mirrors, and we can control the mirrors with computers. So we can do 3D acquisitions of all kinds. We can put the sample on rotational or translational stages, either of the source or the receiver, or a combination thereof. So we could program things and come back with very rich data sets the next morning. What I'm first going to focus on is that this laser is slightly dangerous for your eyes, but also for hitting things. If you crank up the power, you could drill right through most of your samples. So we generally do this at low laser powers or a diffuse beam. So everything I'm going to talk about is in the first part of this talk, is in the linear regime. We're going to keep this power down so that after the wave pass, the medium is goes back to its original situation. Much of the assumptions we mostly make in seismology for seismic waves. So one of my favorite experiments is this one, and somebody pointed out on the AgroDAS website, there's some mention of investigating apples. Here we investigated apples too. And so what we did here is we measured the wave field of an apple, not just in transmission mode, but for every angle and to go around. We got all measurements around the whole epicenter of the apple. And here you can see a P wave, and then here's a surface wave coming all the way to the antipode of the apple. And the waves don't stop there, they go around the other side and they go back, and we have many of these laps around. And that looks very much, we thought, oh, that's like I've seen that before. Here's for example, a Tohoku earthquake, where you can see that same feature here. So from this earthquake here, these are the stations that I downloaded and then ordered them by distance. And it looks somewhat like our apple, except the time axis is way off, right? And so if you take one of these stations and take the Fourier transform, and then you can see here for the Earth, you see the modes of the Earth appear from the Tohoku earthquake. A couple of important ones. The one with the lowest frequency is the rugby ball mode or football ball mode. I now live in New Zealand, so it's the rugby ball mode. And so you get extension at one half period in one direction and compression on the other. And half a period later, it's vibrating in this direction and it's narrow in the other. And this one here, 0S0, that's the Earth increasing in size volumetrically, and then reducing half a period later as a whole. So this is called the breathing mode. In the Earth, the breathing mode is at a higher frequency than the rugby mode or the football mode, and that's because this is more sensitive to surface waves, where the velocities are. I'm just saying it backwards. This is sensitive to the body waves, and our body waves are relatively fast in the Earth compared to the mode that's more sensitive to the velocities near the surface. In the apple, we also get those modes, and we can identify them. We modeled them, and the first mode is actually the breathing mode. So the apple expands as a whole and contracts ever so slightly. And that's because the apple, the core of the apple is different than the core of the Earth, in the sense that we have seeds and even air there. So it's actually a low velocity area. And so you see that mode first. All right. And so you can also then just take one measurement a day. And what is the other thing? Eat an apple a day, and then that keeps the doctor away. But if you take one apple measurement a day, then you can see how the velocities change and the attenuation increases as the apple ages. So other tabletop measurements, I'll call them tabletop because, yes, question. Yeah. Or do you see like focusing of the wave field? Probably, but we cannot coexist the source and the receiver exactly, because then we get some of the interference in light. Yeah. Or the antipode, we get the focusing for sure. Yep. We also do medical imaging. Years ago, a master's student started doing photoacoustic imaging. She was really keen and knowledgeable about the medical field. I said, I know nothing. I only have lasers. She said, that's okay. I'll take care of the medical aspects of it. And after actually doing postdoc in Langevin, she's back with us now. That I'm really excited. Jamie Johnson is now Jamie Shepherd. She got married, but this is some of her work for her PhD, where she used photoacoustic imaging. So now that strong pulse laser is actually focusing inside the body, and we have a tunable laser, so you actually have every color of the rainbow. And if you go through these colors, you can actually pick certain aspects of the human body where you get a maximum expansion. And then we use one-way wave propagation, kind of like an earthquake, one-way wave propagation to do the imaging. And so this is the ultrasound, and you can see the top of the carotid artery. It's a very important one, I was told, here in the neck. And this is of a deceased person. and that is the top wall. Here's the bottom wall. And here, this person had issues in their arteries, a buildup of plaque, and the way the human body fights that, they said, "Oh, we got plaque. I'm going to rupture. I'm going to rupture this vessel wall. So let me put in some reinforcements." And so you actually get calcifications on the walls of your arteries, which also can become a problem eventually. And here you can see some of that plaque light up from the photoacoustic signal. So this is ultrasound, the bottom and the top wall, and then the red is the photoacoustic signal. Of course, the ultrasound really likes that calcification. That's a huge impedance contrast, so they really stand out in the ultrasound. And it's an artifact here due to that calcification. Okay, so now we'll get to rock physics. So we did this for years, and we would go to meetings, AGU, SEG, and say, "We got this measurement, we can measure your rocks." And it turns out very few geologists are interested in our measurements at atmospheric conditions. They want to know the behavior of the rocks at depth. So we had to kind of retool. Doing measurements of rocks at atmospheric conditions only got us so much forward. So let me first tell you where the samples are from that I'm going to present. This is the Alpine Fault. So this is one of the main geologic features in New Zealand. You can see the expression here. It's mostly a strike-slip fault, but it has a vertical component to it that has over time built up the Southern Alps. So not the Alps, but our version of the Alps. They're almost as high, and they're also really beautiful. But we're very concerned about when this will erupt again. It's been shown that it's fairly consistent at 330 years on average for a new eruption of magnitude 8, maybe bigger. And it's been more than 330 years. So we're due in New Zealand, so there's a lot of interest in understanding this fault. So here's some samples from the hanging wall of the Alpine Fault. Here is the police lineup of the samples we'll use today. And so this is in decreasing distance to the fault. So the fault is in a schist, and the closer you get to the fault, the more affected it is by previous earthquakes and just tectonic processes. So that schist gets slowly but surely mangled up by the fault till you get almost at the fault. We call this the cataclysite. And that is a highly damaged material. It's only one small step away from fault gauge. So now we're into Jonathan Simpson's work, and he did some amazing things, not just in measurements, but also advancing the capabilities of our lab. So we actually bought a pressure vessel and then had it retooled for our lasers. So these are 1-inch sapphire optical windows. So now we were able to do measurements under pressure with the same laser system. And not only that, we also are able to either heat the sample to about 150 to 200 degrees. And now, more recently, I don't have any examples of that, we can also have basically turned this into a freezer. And then now we're starting to do rock physics for Mars analog rocks. And if anybody's interested in that, I'm happy to talk about that over lunch or something. And so we're doing rock physics measurements on those as well. Okay. Jonathan also installed his master's project was to play around with the idea of having a rotational stage inside the pressure vessel at high pressures. So we don't have a lot of research funding in New Zealand, so he basically started and ended with parts of a 3D printer that he put in there for the rotational stage. And it turned to be extremely robust. It maintained as high as the pressure as we can put in our rocks. So what that allowed us to do is to look at the anisotropy in the rocks. And as you'll see in a second, these rocks from the Alpine Fault are very anisotropic. So we can take a measurement at every angle, at pressure, at temperature conditions. Why is it now important, and why did the geologists not care so much about our stuff beforehand? Because in the olden days, we would do measurements like this and go, wow, your rock's really anisotropic. This is the angle with the direction, the spin, and this is the time axis. And you could see the P wave arrival would change, well, almost a factor of 2. And so you'd say that's really anisotropic, and I think it's because of the banding and maybe a bit of microfracturing. But when you pump up the pressure in the vessel with gas and repeat the experiment at 16 megapascals, which is the equivalent of one-ish kilometers of depth, hydrostatic pressure, then the anisotropy is much less. And so we have closed some of the fractures, the microfractures, that if you're at 1 kilometer depth, those would be closed anyway. And so therefore, we can now say what we think the anisotropy would be at 1 kilometer. And that would be interesting for us seismologists, because now you can use your imaging techniques to get a much better image of the alpine fault at depth. Okay, so these are the Rose diagrams. So in the center is 0 velocity, and then on the outside is 5,500 meters per second. And then and this is the angle by spinning the sample. And these are the 5 rocks we had, and so they're all anisotropic. So the velocity depends on angle, but you can see the light colors are low pressure, and then the darker colors is towards the high pressure. And you can see that some of these, this schist, it doesn't worry too much about the increase in pressure, because the velocity doesn't change much. So that doesn't have a lot of microfractures to be closed. But as you get closer to the fault, you can see, this is the most extreme one, you can see that the cataclysite changes velocities a lot. So there's a lot of microfractures. You can also see that it consistently changes all the way around the angles. So this means the microfractures are actually randomly oriented. Yeah, so the anisotropy comes from the banding in the rock, but the microfractures may or may not be oriented with the banding in the samples. So if you model this, now we can't model this like grain for grain, so we do use a effective medium modeling technique, but we can put the constituents of the grains in, get an effective medium velocity, and then add voids to represent the microfractures. Then you can see here for the cataclysite, this is at high pressure, this is at low pressure. You can see that they shift as a whole because of the closing of the microfractures. And we've closed 10% of the microfractures in that first kilometer here, because we used to have about 3.3% of these fractures, and the best fitting model at high pressure is 2.7% of the microfractures. So then we can turn that back into kind of a cartoon on what we think the anisotropy and the microfracture distributions look like as a function of distance to the fault. And we can give that to the seismologist and say, you might want to use this in your inversion techniques to get the highest resolution image of the fault. You can also give that to the fault people and say, okay, here's what we know about if and when the fault's going to rupture. So for rupture processes, this is valuable information. So far, though, we've kept the displacement low. Like the typical threshold is 10 to the minus 6 strain. That's the kind of where we said, okay, if we go above that, we have problems. We need to stay below that for linear systems. So we like problems. So yeah, go on. Yeah. In the middle of the fault. Oh, here. So this is a representation of the microfractures. It's not isotropic, but the microfractures were isotropic because the entire velocity shifted as one. So it wasn't, if the microfractures were aligned with the axis of the anisotropy, then we would only change one of the velocities. We wouldn't change both the fast and the slow velocity. Yeah. No, there's no shear component. This is hydrostatic pressure. Yeah, that would be nice. We don't have a rig for doing shear component measurements. Yep. Yeah. Exactly. The closer we get to the fault, the messier and the more damaged the rock gets. And as you get really close, it's damaged in all directions. Okay, so I'm not going to spend time, sorry, Florent, but everybody already explained your figure here. But this is just to illustrate, I didn't know this was going to happen, so I put it in, that there are going to be cases where waves pass and they have of a high enough amplitude that things are no longer linear. And so I also added another example here from after the Denali earthquake. There's triggering of tremor at Parkfield, and you can see that this is the conventional seismogram. There's the P wave, S wave, and the surface waves. And especially during the surface waves, you see if you look only at high frequencies, you can see tremor being generated, dynamically triggered. The keyword is dynamic. It's because of the change in the displacements, the high displacements from the surface waves that trigger tremor in Parkfield. So this is another way of saying there are nonlinear things going on in the Earth that we should study. A third way, and there's some poster, at least a poster out there, and maybe more, is we can use pump probe techniques to look at this. So if you have a rock and you stick it between two things and you slowly move this, well, in our case, this is, I think, 10 hertz or so. And you squeeze the rock here, and you send a wave through the axis and measure the velocity across the rock, then you can see that the velocities, like anti-match, so this is dilatation to the top and compression to the bottom. You can see that when there's maximum dilatation, there's minimum velocity, because you just basically stretched and changed the stiffness of the rock. And so when you get maximum compression, then you get a maximum in the velocity. But it's not really the maximum in the velocity, because before we turned the pump on, the velocities were sitting here. So this constantly changing the stresses on the rock did a number on this rock, because the velocities, even in the strongest compression, are lower than before you did those compressions. So we damaged the rock, but not to worry, when we stopped the pump, this rock healed itself again. And after an amount of time, it is back to the original velocity. Yep. Yeah, I'll get to that. So that's a really good question. Like, what is damaging and what does this damage look like? We don't, the honest answer is we don't fully know, but there's a model by Roel Snyder and Christofsen Schoenfelder where they looked at this, and they look at breaking bonds. So we think that by rattling this rock around, some of the bonds at the grains or maybe at the microfractures have temporarily come loose, and the velocity through them is less. And those bonds are remade in time, and then you get back up here. I'll say that again, or hopefully it's more clear in a little bit. Another way to look at this nonlinearity, as I promised, is we're gonna live on the edge and turn the source laser up slowly to maximum power. And so then you get a larger amplitude of the wave field. You think all's good. But if you look in the coda, now you see these phase shifts happening in the coda, and we get small velocity changes. So we don't need a pump and probe system to explore these nonlinear properties. We can do our own damage of the rock as we propagate the waves through them. Yeah, so this large amplitude wave then damages the rock, and in the coda we can measure that velocity change. Yep. No, but that's a good question. It's not a change of temperature. Even though we put a lot of energy in, it's for a few nanoseconds, and the repetition rate of our laser is only 10 hertz. So we've done the calculations with what the temperature of our sample how that would change it, and it's negligible. In fact, Dylan did some measurements on ice cores in this same way, and everybody said we were going to melt the ice cores, and we didn't. And he hates me saying this, but we have kept them so long that we ended up drinking margaritas with the ice when we were done. That's how long it was, I think, 1 million-year-old Greenland ice, I think. Yeah. In the ice? in the rocks. If we can focus the laser, and I can drill a hole where you can look through if you want. This is only strong enough so that we create damage that heals again, as I'll show you in a second. So we're not going to the level where we actually create fractures that are permanent. Yep. Okay, so here are samples again. Remember, the schist and the mylonites were relatively far away from the alpine fault. They don't show much of that effect that I just showed you on that previous slide. That was for the cataclysite. So the cataclysite is more prone to this nonlinearity than the competent rocks further away, which goes to show you that the answer of what's going on at the microscale must be related to the fractures that already exist. So the bonds that exist on the microfractures are temporarily damaged here. And they're on the order, the scale here, this is the elastic modulus. So if you want to turn that into a velocity, you just have to square that because the velocity is proportional to the elastic modulus squared. So these changes are small. They're on the order of 1%. But if you have, say, a fault that is fully loaded already, this could be the type of change that tips it over the balance. And in fact, there are lots of examples of this, where a big earthquake traveled 1,000 kilometers and then dynamically triggered an earthquake elsewhere. It's hard to prove, so you have to do this basically statistically. And you see that you have many earthquakes far away, more than you would in periods where you didn't have the big earthquake triggering these. But now the geologists and geophysicists come nagging, like, that is at atmospheric pressure. What happens if we increase the pressure? Well, then these are two cataclysite, but basically the same result. As soon as we go up in pressure, or even at 5 megapascals, we have basically pushed those microfractures closed again, and we don't get that nonlinearity anymore. So you could stop here and conclude, well, these nonlinear effects will only be near the surface. But we didn't stop there, because not only in depth will the pressure increase, the velocity or the temperature will increase as well. So these are just, we measured the velocity very carefully, and I'll explain, I think it'll be really clear why I focus on very carefully. We measure the velocity very carefully as a function of temperature in the cataclysite. And you can see that the velocity changes on the order of 10%. So just temperature itself weakens the rock by a large amount, in fact much larger than the nonlinear effect does. Why did I say very carefully? Because we figured out something accidentally. This is not in the cataclysite, but before we were going to do nonlinearity as a function of temperature in the cataclysite, I had a feeling it was going to be complicated. So Jonathan and I decided to first investigate a Berea sandstone. Again, if you're a rock physicist, this is one of the go-to rocks because it's almost pure quartz, very little complication. So it's the simplest rock. After glass beads, you go to something like a Berea sandstone. And what do we find? This is now the velocity. After we changed the temperature from 50 to 60 degrees, the velocity initially drops, and then it recovers. So this says that the velocity, after we increase the temperature, the velocity drops. You can say, Kasper, you just showed me the previous graph that if the velocity increases, the velocity drops. What's the big deal? Well, the big deal is if you go from 60 to 50 degrees, the velocity also initially drops and then recovers. And so that means that these nonlinear effects only need a change. They don't care about the sign of the change. If you mess with a rock, initially it'll be damaged. You can mess with it with pressure, you can mess with it with temperature, you can mess with it in a whole host of ways. You first see a negative velocity change. And so therefore we computed, this is not the absolute temperature, but it's the temperature gradient, because it's the temperature gradient that matters. It's just like it is the strain rate that matters to get these nonlinear effects. And that's why in the previous plot, we went very slow to measure the absolute velocity as a function of temperature to avoid this effect. So then we did multiple cycles of this, up, down, and always everything you do, you get first a drop, then a recovery, then you change the temperature, you get a drop and a recovery. And then those are the dots here. The lines are the model. And I figured I wouldn't get into the theory of this, but this is a model that that is based on broken contacts. So if you change something, the temperature, the pressure, you disturb the rock, you break the contacts. The easiest ones to break are the ones that were already near microfracturing. And that's why the cataclasites are the most non-linear. But you can now get an idea of what percentage of the available bonds in a rock are broken in a rock or in any other medium. And the data fits. You can make the data fit really nicely. Pardon? Yes, yes. And basically, each kind of bond recovers exponentially, and you have a number of them, and you have some that are recovering fast and some that recover slow to come up with a cumulative effect like this. Yeah. Okay, so then we said, all right, fine. We do now our nonlinear experiment by cranking up the temperature, the volume of our laser, and then we do that at every temperature. And as expected, when the rock is hot, statically hot, so it's been hot for a long time, it was already had a lower velocity, i.e. was weaker. We have a stronger effect of this nonlinearity with depth. And so what you see here now is the greatest nonlinear effect is now on the order of 4%. So that's not really fair because now we need to add the pressure, right? When you go down, the pressure goes up and the temperature goes up. So can you just add the two, right? Is it just the pressure makes it the nonlinearity less, the temperature makes it more? Add the two, see where you end up. And the answer is no, it's slightly more complicated than that. So this is the old measurement here, where the temperature goes down, and this parameter alpha. So you can measure this in a change of velocity, a change in the modulus, or you can do it in this weighted change of the modulus, but you average it by the absolute strain. So that way you can compare these lab measurements to field measurements, because it's kind of like a normalization. But you can read this as just the strength of the rock. So just in pressure, the strength of the rock drops down to 0 quite quickly at maybe, I don't know, something like 400 meters. For us, it wasn't measurable anymore. If you just do the temperature, it goes up, but not just consistently up. At this depth here, at atmospheric pressure, we get a phase change in the leftover water in the rock. So there's more complicated than that. And that phase change doesn't happen when we pressurize the rock, or it happens somewhere else. So when we do pressure and temperature, we get a much more consistent result where the decay in the nonlinearity is much less than just in the pressure event. So we think that this nonlinearity persists way deeper than that. And we know it has to, right? Because if we had dynamically triggered earthquake somewhere out 1,000 kilometers away from a big earthquake, that means they have been, there's effects of that at the nucleation depths of these earthquakes. So we know these nonlinear effects must persist to greater depths than just near the surface. Yeah. Pardon? Oh! Yes, thank you. I was about to forget, and then I would have to go back. Yes, we didn't just do this on the cataclysite. We also, right before the eruption of Fakari White Island, we collected rocks on the volcano. And so we took one of the volcanic breccias, which remind us, I'm sorry if I insult the volcanologists, but they look for us like the cataclysites. And so they're also very damaged from eruptions and other processes. So that's another damaged rock here. So it's very important that both the damaged volcanic rock and the damaged fault rock behave in this nonlinear fashion. Thanks for reminding me. The star. Yes. I also should mention that here. Gosh, thank you. Like, you're helping me out. The one parameter that we need to understand better, and that is not included in this study, is water. So everything I've told you today is for unsaturated rocks, and we know in situ there will be water available. So this is our one measurement where we saturated the sample because it's the easiest to do. It's at the surface. And so we can see here that the nonlinear effect is much higher than for our non-saturated rocks. So one of our conclusions from this study is we really need to sort out how to get some fluid lines into our vessel and also perturb the fluid content in these samples, because it's going to be an important topic, and it may mean that this green line will actually even be higher and that the nonlinear effects will be greater. Yeah. Okay. So for dynamic weakening and natural hazards then, Jonathan made some conceptual pictures on why this is important. One of the ways, there are many reasons I think why nonlinearity could be important in the Earth. But one simple way is, if the Alpine fault ruptured, for example, we expect large seismic waves nearby, obviously, and those are actually going to be conditioning the part of the fault that hasn't ruptured yet. So that means that we locally and temporarily get a reduction in the shear strength of the fault here. And that means this fault can rupture further than you would predict from previous rock physics measurements on the materials in the fault. Because we all know from our textbook that the seismic moment will be, the area of the fault times the displacement times the shear modulus. But that shear modulus is actually lower in a dynamic case. In the volcanic case, this is maybe, I thought it was going to be a little bit of a harder sell, but volcanoes, as magma comes to the surface, we're hopefully warned by seismic events. But those seismic events could weaken the plug in some of these volcanoes, and actually the precursory seismicity could help in making these volcanoes come to an eruption. I thought that was going to be tough, but I don't have it in here, but there's a paper by my colleague from Wellington, Finn Ilsley-Kemp, where they didn't show an eruption, luckily, of the Taupo volcanic field, but they showed dike intrusion and related that, or claimed that would be related to dynamic weakening from the Kaikoura earthquake, the latest large big earthquake in New Zealand. All right, so just the final take-home messages. Why do we measure waves in the lab? Well, one thing is to test new physics, which is very exciting. We've seen examples of time reversal. I talked a little bit, but I didn't show radiative transfer developments. I didn't mention Coda wave interferometry, but it's amazing to see all these examples of Coda wave interferometry. And when I came as a graduate student, that was hot and new and very exciting. More recently now, we saw Alex discuss matrix methods, so there's a role to play in labs to test some of these new ideas that are done in theory and maybe numerically. Then there's a role for ultrasonics in the lab to probe small, not important, physically small problems like medical imaging and non-destructive testing. We knew that in fruits, but we've also done that in timber and other materials, and so there's a role for ultrasound there. And finally, if we get the conditions right, we can help calibrate large field scale problems in seismology. So rock physics for earthquake and volcanic processes, both for the imaging and for the explanations of the dynamics. And so I think with that, I would like to stop, and I'll leave the last one up so dark, but thank you very much.